Hi there, I'm Mehdi Salehi, master student in Concordia University in Montreal, Canada, and I'm very excited to share our recent research entitled of Immutability versus Upgradeability in Ethereum, Myth versus Reality with you in BTS conference. And I should say that this is a joint work with my supervisors, Dr. Jeremy Clark and Dr. Mohammad Mannan. In software engineering and software maintenance, we have two important concepts. Updates happen when we need to correct faults or bugs, but upgrades happen to improve code and add new functionalities to our code base. Smart contracts are pieces of code, or better to say, bytecode, that's supposed to be immutable. By immutable, I mean no one can change them like in the future. But a piece of code that is not upgradable is risky, right? In blockchain is even worse than traditional softwares because smart contracts have control over billions of funds in their custody. So no way we need to add upgradability feature to our smart contracts, but two main important questions raised here. How to add upgradability, however we have immutability, and also who will be responsible to decide on the changes of the system in future. This is a big picture of different upgradability patterns in Ethereum right now. We classify different patterns into two main categories: retail changes, in which one can change a small pre-specified part of the dApp, and wholesale changes, by which one can change the whole logic of the system. In this talk, we just focused on delegate call-based pattern, which is the most popular pattern in the Ethereum right now. But in the paper, we explain all different patterns in the Ethereum in detail. I suggest to read the paper for further details. In delegate call-based patterns, the user is supposed to send transaction to a storage contract, also known as proxy contract, and the proxy will delegate call the message to a logic contract, also known as implementation contract. Delegate call is an opcode in Ethereum that preserves the context, and it's very similar to copy pasting the code and running it on the context of that specific contract, but it's not the same. It's not exactly the same copy pasting. In the upgrade event, admins must deploy a new contract and change the target address inside the proxy and let it know that it should delegate call into the newer address. The pros of using proxy, the delegate call based pattern, is that one can update the whole logic of the system and there is no need to migrate the data. And also it's very easy to add this pattern to a regular code base. Also, user endpoint won't be changed. And this is why this pattern is very popular in the community. But the disadvantage of using this pattern is there is a gas overhead for transaction because of the indirection happen between proxy and implementation contract. Also, there is a risk due to using delegate call opcode, and also you cannot change the state of contract after deploying the proxy. We summarize all methods and evaluate them in the paper, and we differentiate them as a designer point of view. Our main goal in the next part of the research is to find contracts that are using delegate call-based pattern or proxy patterns in the Ethereum blockchain. For doing that, to find delegate call-based smart contracts, we use data of 1 year by getting the transaction traces of 2 million blocks of Ethereum blockchain using an Ethereum full archival node. To describe our methodology, let's dive deeper into the proxy contract itself. The proxy contract is very similar to this snippet code. There is an address, we named it implementation or imp address here, and there should be two main functions, fallback and upgrade function. Fallback functions is a specific type of function in Solidity, and it will be executed whenever user send a transaction to the contract, and that function doesn't exist in the contract, so fallback will be called. And also in the proxy contract, in the fallback there is a delegate call into implementation address, which will forward the whole message into the implementation. Also, as we said, there should be an upgrade function, by which the admin can just change the implementation address. So to find proxies, we first check all transactions that we have to find those contracts that passes the transaction and like the transaction passed this specific type of fallback. And if we found those contracts are proxy, but not all proxies are upgradable. And we need to find the upgrade function as well to be sure that this proxy is upgradable. And for doing that, we decompile the proxy contract and use a static analysis to find a function that the admin is able to change the imp address inside that function. If we found this type of function inside proxy, we mark them as regular upgradable proxy contracts. But there is another type of proxy contracts which named UUPS proxy contracts, in which the upgrade function resides in the implementation and not in the proxy. So to find them, we just decompile the implementation contract here, not the proxy, and try to use the static analysis to find upgrade function inside the implementation. And if we found it, we mark them as UUPS. Our results showed that we found 1.4 million proxy contracts, and by filtering them to just find unique proxies with unique implementation contracts, we come up with 13K proxy, and 7.4K of them are regular upgradable proxy contracts, and 403 are UUPS. To answer the second question, the type of admins, like who will be responsible for the future changes. We have three main types of admins. The first one is an EOA, in which just one private key can change the system. The second type is multi-signature wallet, in which M out of N persons can decide to change the system. And the most decentralized solution, or better to say most trustless solution to this admin, is having a decentralized governance scheme. The first two is very dangerous because one or just limited number of persons can decide to change the whole logic of the system. Here our goal is to find the type of admin of 7.4K proxies we found in the previous part. First, we find a place where the admin address is saved by access control check. Then we check that if that address is an EOA or multi-signature or another type of contract. Totally, out of 7.K regular proxy contracts, around 50% of them are controlled by just an EOA, 13% are controlled by a multi-signature wallet, and this is an alarm to Ethereum community because, for example, EOA admins are very dangerous because a single private key can decide to change the whole logic of the system, and a malicious or compromised EOA can change the system and like even steal the fund. And there was an incident on Ben Finance protocol in December 2021 in which the admin upgraded the system into a backdoor version and take profit from it. However, the community considered using a multi-signature admin as a safe option. We want to say that this scenario is not true, and like a limited number of persons can just take control of the system. The other problem is that the addresses on Ethereum is pseudonymous. Nobody can prove the identity behind the address. So a malicious team can keep enough keys in their hands to sign any transaction they need. And like in this scenario, the multi-signature is equal to an EOA. And we have this recent attack on Ronin bridge, in which 5 different private keys are leaked. The key takeaway of this research is that immutability, decentralization, and trustlessness is oversold in Ethereum blockchain because of widely usage of upgradable smart contracts. Also, more than 60% of these contracts have EOA or multi-signature admins. Also, it's worth mentioning that the mechanisms we used in this research to find proxy patterns and admins are generic and not just sticking to the artifacts of a specific library, such as, for example, Open Zeppelin libraries. Thank you so much. You can get in touch with me if you have any suggestion or question, and you are more than welcome to send me an email or ping me on Twitter. Thank you.